In this video, we're going to be talking about aldehydes and ketones. And we have alluded to these a little bit already in the class. And in fact, if you recall working with secondary and primary alcohols, we've already seen how these can be formed. So aldehydes and ketones are really common in everyday life. Formaldehyde is just one example of an aldehyde. And of course, that's, kind of some embalming fluid or formalin, which is formaldehyde in water. And so we really have a lot of usage for our aldehydes as well as our ketones. So propanone, or otherwise known as acetone, of course, is a solvent cleaning fluid and also nail polish remover, rubber cement. So these are just some examples of aldehydes and ketones in everyday life. So we might have some really pungent or even really good smelling fragrances that are related to aldehydes in particular. So the smell of almond, vanilla, cinnamon, these all are in relation to these aldehyde functional groups, which we're going to go over in this video. So aldehydes and ketones are both grouped into what's called a carbonyl category. So carbonyl group basically means that we've got a carbon somewhere in our backbone chain that has a double bond to an oxygen. And so here we can see how our carbon double bond oxygen carbonyl group can be classified either as an aldehyde on the left or a ketone on the right. And the difference is its placement within that backbone. So if it's at an end where our carbon that's bound onto our oxygen has a hydrogen attached also, then we have an aldehyde. And I like to think that the word aldehyde has an H in it, and the carbon, the central carbon in an aldehyde, has an H on it. If we compare that to a ketone would be somewhere in the middle of our backbone. So here's our carbonyl with our central carbon of interest. And on either side, there's another carbon bound. So there is actually no place for a hydrogen to be bound on here. So that actually plays a role in the types of reactions that it can undergo and what can happen to it. So an aldehyde at the end, where we have a hydrogen also attached to our central carbon of interest. Ketone somewhere in the middle, where there is no hydrogen attached to our central carbon. Now this carbonyl, whether it's in the form of a ketone or an aldehyde, this carbon-oxygen double bond is polar. So it is a polar covalent bond in which oxygen is more electronegative than carbon. So when we're playing that electronegativity tug of war that we talked about in the last class in Chem 104, oxygen can't completely pull electrons towards it, of course, but we have that partial negative charge on our oxygen and a partial positive charge on our carbon. And that's going to play a role in its ability to form different types of bonds with, for example, water. So let's get into naming. Naming aldehydes is pretty straightforward. We're going to use the identification of our main chain carbon backbone, and an aldehyde will end in an Al. So if you think of aldehyde starts with an Al, then this item would end in an Al. Okay, so some examples How many carbons are on this item? Here's our carbon. This goes to a hydrogen, this goes to a hydrogen, so there's only one carbon here. So methanal. So methane, drop the E, add an AL, methanal. 2 carbons on our chain, so here's the first and the second. Of course, that's backwards. Here's the first and the second. Ethanal. Ethane, drop the E, add AL, ethanal. Propanal has 3 carbons. Butanal has 4. And notice that I'm including the carbon that's attached to the oxygen double bond. So that counts as one of the carbons in my backbone. So here butanal has 1, 2, 3, 4 carbons. Okay, if it happens to be attached to a benzene, then it would be benzonaldehyde. So benzenes always throw a kink in things. Benzene has an aldehyde on it. Let's just call it benzonaldehyde. Naming ketones is quite similar. Here though, let me go back and highlight something. Because an aldehyde always has to be at the end. Remember, we have to have a carbon, double bond oxygen with 1 carbon on one side, and it has to have a hydrogen on the other side. It's got to have at least 1 hydrogen in order to be an aldehyde. This has to be at the end of my chain. So the aldehyde functional group will always be at the end. We'll always count that as carbon 1. If aldehyde is our highest ranking functional group, then that's always going to be on carbon 1. So I start carbon 1, 2, 3, 4. Ketones, of course, can't be at the end of the chain because a ketone has to have a carbon on each side of its central carbon. So here we'll count the number of carbons in our main chain. So identify our main chain first, count the number of carbons. In this case, there are 3, so it would be propane. Drop the E, add an one. So ketone, I'm going to add an one. So propanone. We also technically need to go back and count which carbon it's on. So if we start from the left, 1, 2, 3. If we start from the right, 1, 2, 3. Of course, in the case of propanone, it has to be in the middle. It has to be on that second carbon. So it will always be 2-propanone. But we'll see in a minute more examples. And then, so we've got some really common names, but we're sticking with IUPAC names, of course. So more IUPAC names. So here was our propanone. Butanone. 1, 2, 3, 4. We always have to count this as the lowest carbon. So we could say 2-butanone, but of course, in this case, it couldn't be 3-butanone. Pentanone, though, we have to for sure give the number. So we've got our carbonyl, so our ketone here in the middle. Identify my main chain, 1, 2, 3, 4, 5 carbons here, my main chain. And I can start from the left or the right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. In this particular case, it doesn't matter. It's going to be 3-pentanone no matter which direction I go. But I have to add the 3 here because I could potentially have the ketone on this carbon instead, or of course this carbon instead. But I need the 3 placeholder here. And I would implore you, and if you have some question as to whether or not to include the number for which carbon this item is on, you might as well include it. Oops. Okay, naming cyclic ketones. So we couldn't have a aldehyde in the middle of a cycle because, of course, any one of these carbons has another carbon on each side. So an aldehyde cannot be in the middle of a circle, but a ketone can. And so here I've got my carbon on each side, my double bond oxygen. So this is, of course, a ketone, and it happens to be on what would otherwise be named cyclopentane. So I'm going to take the cyclopentane, my main chain name, I'm going to drop the E and add none, cyclopentanone. So for the item on the right, I've got what would be a hexane, and drop the E. So cyclohexane, drop the E, none. So cyclohexanone. I've also got a methyl sticking off. And in this case, I'm going to start counting at my most important or my most functional group, my most reactive functional group, my most oxidized, where the oxygens are, functional group. And that's going to get the number 1. So in this case, I can count clockwise or counterclockwise. Let's see what happens. So, excuse me. So if I go counterclockwise, I have 1, 2, 3, 4, 5, 6. And this would be at the 5 position. But if I go clockwise, 1, 2, 3, 4, 5, 6, then it's at the 3 position. And that's, of course, what we actually want, the lower of the numbers. So we're going to call this 3-methyl cyclohexanone. Okay. So let's talk about some properties of aldehydes and ketones. And these are going to, again, come into play with their ability of hydrogen bonding to either another of its own molecule or hydrogen bonding with water. And if you remember, the bond within the ketone itself or aldehyde itself, so the carbonyl, is partially charged. So our oxygen is partially negative charge and our carbon is partially positive charge. So now in the case when we try to put this into water, we can use our carbonyl's partial negative oxygen and hydrogen bond with the partial positive of water's hydrogens. So at room temperature, we're going to have the smaller, so the lower carbon count aldehydes in gas form. Ketones and aldehydes that have 3 to 10 carbons would be liquid at room temperature. And this is, again, about dealing with their ability to form hydrogen bonds among themselves. And of course they can't, but they could form dipoles. So let's see what that looks like. So ketones have the ability to, again, form these dipole-dipole interactions. So if this is my ketone, I've got carbon chain to the top and the bottom. And so my ketone, the carbonyl, is sticking out here to the right, to the side. And nearby is another replicate of the same molecule. So on oxygen here, I've got a partial negative charge. On carbon here, I've got a partial positive. And so they can form a dipole interaction in between them. Of course, this is not as strong as if it were a hydrogen bond in between them, but still somewhat effective. So that would give them a slightly higher boiling point than an alkane of the same length chain, so the same number of carbons. And it would have, though, lower boiling points than an alcohol of about the same size. And that's, of course, because alcohols could form a full hydrogen bond in between molecules, and these can only form dipole-dipole interactions, which are not as strong. So they can't hold close to each other as tightly and as effectively. So it's much easier to throw a couple of them off into the atmosphere and boiling. So you can see the boiling point increases, though, even with, even in this case, we've got butane, which of course is 4 carbons long. We've got propanol here, which is only 3 carbons long, but about the same molar mass. Propanone, a slightly higher boiling point, and then alcohol of about the same mass is a much higher boiling point. Okay, and so then when we're looking at their solubility in water, here we're looking at their ability to form hydrogen bonds now. They can't form hydrogen bonds amongst themselves because there's no hydrogen involved in a polar bond. So there's no partially positive charged hydrogen on our aldehyde or ketone molecule. But if we enter water into the mixture, now water's hydrogen has the ability to hydrogen bond with our partially negative carbonyl, whether it's a ketone or an aldehyde. And so that makes it more soluble than a similar alkane. And in general, we have a rule that even though hydrogen bonding can occur, anything that's about 5 carbons or more long will have a much higher hydrophobicity. So the hydrophobic portion of the molecule between those carbons and hydrogens, that nonpolar region, would outweigh the ability for a hydrogen bond to form in that one carbonyl spot. So if it's 5 or more carbons in your backbone chain, typically now is not as soluble. But these really small, 1 to 3, maybe 4 carbon aldehydes or ketones, those ones can dissolve in water. Okay, so we're going to end there and pick back up in the next video with oxidation and reduction reactions for these aldehydes and ketones.